Hello everyone, welcome to SPEc eLearn, the online learning channel dedicated to chemical engineers. In this video, we are going to have a discussion on chemical reaction engineering. In part 1, I will walk you through the insights into reactor design. By the end of the course, you will have an understanding of residence time, reactor volume, space velocity, and its significance in reactor design. Chemical reaction technology has evolved over the years, from the initial development of Haber-Bosch process for ammonia synthesis. Chemical reaction analysis is based on two pillars. 1. Reaction analysis. 2. Reactor design. In reaction analysis, the stoichiometry, thermodynamics, and kinetics of chemical reactions are studied. Stoichiometry enables us to take an account of the interaction of the various chemical species in the reaction. Thermodynamics points out the limitation on chemical conversion. Kinetics provide information on how fast the reaction can proceed. We will now move on to the reactor design insights. The most important term is space velocity. Residence time or contact time in the reactor is a measure of reactor size. Broadly speaking, the key design parameters include reactor volume or catalyst volume, catalyst life in heterogeneous catalytic reactor. Take a look at the figure. Two reactors are shown, one a simple PF4 and other a catalytic PF4, a heterogeneous reactor. In the reactor, A reacts to form product B and C. The reaction is reversible and the conversion is limited by equilibrium. Accordingly, the reactor outlet has A, B and C. Assume the conversion is 40%. We need to size the reactor for a feed rate, say 100 cubic meter per hour. To answer the question, one should know what is the acceptable residence time. Residence time is a ratio of volume of the reactor to the inlet volumetric flow rate. This is an apparent residence time. The true residence time calculation is complicated since the volumetric flow rate and the rate of reaction at each position in the reactor depends on the temperature, the pressure, the concentration of the reactive mixture. Volumetric rate of feed is fixed by the capacity of the plant to be designed. It is decided by the end user. How do you determine the volume of the reactor? It is usually obtained from the lab trials. In fact, It is a residence time that is important. How long the reactants and products can remain in contact in the reactor. Several factors are considered during lab trial. Nature of reactions. The reaction may be exothermic or endothermic, product degradation, or conversion to byproducts. Many a time, the product formed can undergo further reaction with raw material to produce byproducts. Catalyst deactivation in catalytic reactor. How fast the reactant and the product move out of the reactor is a key to the reactor conversion and stability of the reactor. Longer the product B stay in the reactor, the more it may degrade. Longer the reactants or products stay in the reactor, higher will be the temperature rise in the exothermic reaction, affecting equilibrium conversion. In adiabatic endothermic reaction, the temperature drop will be larger, affecting the conversion. Or in a coke forming reaction, the activity and the conversion will reduce fast if the reactants stay longer. These things cannot be simulated by process modeling. Actual operating data is required to get the first-hand information about the nature of reaction and required performance metrics. The data collected in the lab trial is validated by conducting the same reaction in a pilot plant. Here the reactor and the associated downstream equipments such as separation units are operated on 24 hours basis and hourly operating data and lab reports are collected. During the study, various choices for the reactor types such as fixed bed, fluidized bed, plug flow and CST are considered. This becomes a basis for the reactor design. From here on, design for demonstration plant and finally commercial plant is developed. This figure illustrates how the design development of a reactor takes place from a lab scale to a large scale commercial plant. Scale up of the reactor is done to get performance data so that process nature in terms of operability, reliability and safety are established. Processing rate is maximized. There is mass flow and superficial velocity in the scaled up demonstration plant. Once the process performance parameters, operating conditions and catalyst volume are established, economic analysis to determine the profitability is carried out. What is a measure of contact time? And how do we specify the reactor in terms of the contact time? Come on, let's move on to find out. Usually, the residence time is expressed in terms of space velocity. In reactor technology, the commonly used terminologies are gas hourly space velocity GHSV, liquid hourly space velocity LHSV, weight hourly space velocity WHSV. GHSV. You have to specify the flow rate. The flow rate is usually specified at standard temperature and pressure. That is 60 degree Fahrenheit and 1 atmosphere. So the GHSV is defined as volume of gas feed at STP per hour divided by the volume of the reactor or the catalyst volume. Liquid hourly space velocity. The flow rate is usually specified at 60 degrees Fahrenheit. LHSV is equal to the volume of liquid feed at 60 degrees Fahrenheit per hour to the volume of the reactor or catalyst volume. Weight hourly space velocity. Weight hourly space velocity is equal to the mass of feed per hour to the mass of the catalyst. Typical units for space velocities are GHSV, standard cubic meter gas feed per hour per cubic meter reactor volume. LHSV, standard cubic meter liquid feed per hour per cubic meter liquid volume. WHSV, kg feed per hour per kg of catalyst. Some of the commonly used reactor types in the industries include plug flow reactor, homogeneous, fixed bed heterogeneous reactor, fluidized bed reactor, tubular reactor, multi-tubular reactor, CSTR, etc. The choice really depends on the nature of the reactants, stability and safety of the process. How does the activity of the catalyst change with time? How do we regenerate the catalyst to regain the activity? Heating and cooling requirements for exothermic and endothermic reactions. What are the safety hazards associated with the process? These are some of the considerations you have to keep in mind while deciding on the choice of the reactor. Residence time and space velocities for some of the established chemical processes are ammonia, fixed bed gas phase reaction using iron catalyst, GHSV 1000 to 5000. Production of ethylene from naphtha using tubular gas phase reaction with no catalyst. Residence time 0.5 to 3 seconds. Methanol production from carbon monoxide and hydrogen, fixed bed gas phase reaction using catalyst, copper and zinc oxide based catalyst, GHSV 35,000. Styrene production from ethyl benzene, multi-tubular gas phase reaction using metal oxide catalyst. Residence time 0.2 seconds, GHSV 7500. Having understood the space velocity and its values in some of the common industrial processes, let us now move on to understand its significance with relation to the reactor dimensions. Space velocity not only influences the conversion in yield by minimizing the side reactions but also the reactor dimensions. As space velocity increases, the pressure drop across the catalyst bed also increases. High pressure drop across the catalyst bed means compressor power requirement increases for recycling the unreacted gas back to the reactor for a given catalyst size and bed diameter. This graph illustrates the relationship between space velocity and catalyst bed pressure drop for various catalyst particle sizes. This is for a typical ammonia synthesis process. You can observe as the space velocity increases, the bed pressure drop increases. Also, as the particle size decreases, for a given space velocity, the pressure drop increases. How would you choose a space velocity with increasing pressure drop? Thus, space velocity is a compromise between pressure drop and reactor diameter. From the pressure drop point of view, lower space velocity is better. That is to say, the lower processing rate of feed. If lower space velocity or high contact time is an issue, then larger diameter of the vessel is the only option. For a given diameter of the reactor vessel, larger GHSV means higher superficial velocity. Reactor orientation. Another alternative available to overcome pressure drop problem associated with high space velocity is a reactor orientation. The alternatives are vertical reactor, horizontal reactor. Vertical reactors is usually the choice when it comes to selecting the reactor type. Most of the industrial reactors in fertilizer and petrochemical industries are vertical reactors. Vertical orientation ensures uniform flow through the fixed bed without any bypassing and dead flow spots where they can accumulate and impact the reaction results. Vertical reactors need less space. They are suitable for mixed phase flow like trickle flow. Illustrated in this figure is a vertical reactor, a fixed bed Kellogg ammonia synthesis process. This is a 4-bed catalytic process with a downflow. Horizontal reactors are wide but relatively shallow. The gas flows down from top to bottom. They are selected to minimize very high pressure drop associated with high GHSV, that is for large capacities. Illustrated in this figure is a fixed bed adiabatic horizontal catalytic reactor, internally refractive lined and externally insulated. The horizontal reactor shown in the above figure operates in a propane digestion plant at a weight hourly space velocity of 1 to 2. Process requirement is high yield of product at high space velocities, keeping the pressure drop with manageable limit. That is to say, the byproduct formation has to be minimized. Assume the weight hourly space velocity of the reactor is 1.8. The weight of the catalyst loaded in the bed is 85,000 kgs. This means the reactor is designed for a feed rate of 153,000 kg per hour. This is a huge capacity. Compared to the horizontal reactor, a vertical reactor in this application needs a large diameter vessel, and the depth of the bed will also be very high. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation on part 1 of chemical reaction engineering. Hope this presentation with narration and animation was useful. Please give your comments, if any, about this course after you finished viewing the video. Share with your friends and colleagues to reach out to a large number of career-oriented professionals and students. Thank you for watching.